chargeback fees just spiked 300%. Customers saw two separate charges for a single purchase. The root cause? The capture endpoint lacked idempotency, so a retry on timeout processed twice. Let's break down why idempotency is non-negotiable in payment systems. Welcome to TheCodeForge. Before we dig into that production issue, let's design a payment system. A payment system is a set of services that reliably moves money. Its core challenges are not speed, they're correctness under uncertainty. The naive try-again approach leads to double charges and lost payments. Idempotency stops a payment from being processed twice when a user refreshes or a network retry sends the same request. The core mechanism is an idempotency key, a unique identifier the client sends with every creation request. Here's a simple idempotency service using a concurrent hash map. The putifabsent method ensures atomic check-in set. If the key already exists, we return the cached result, either waiting for completion or returning the final response. A ledger is the immutable record of every financial event. Every credit, debit, fee, and refund is an entry. The balance is derived by summing all entries, never stored directly. This prevents inconsistencies from partial updates. This SQL creates an append-only ledger table. Each entry has a type, amount in cents, and a reference. The balance query sums credits minus debits. Never update or delete rows, always insert. Payment networks are unreliable. Retries must be safe, meaning the operation is idempotent. Use exponential backoff with jitter, cap retries, and send failed requests to a dead letter queue for manual review. This retry handler loops up to 3 times with exponential backoff and jitter. The same idempotency key is used on every attempt, so the gateway deduplicates. On final failure, the request goes to a dead letter queue. Reconciliation is your safety net. It compares your internal ledger with bank or gateway statements to catch mismatches. Run it periodically and automate alerts for any discrepancy. This query finds mismatches between your payments table and the gateway's transactions. The unique constraint on merchant reference prevents double spend, ensuring a given invoice is paid exactly once. A production payment system has several layers. The API gateway handles auth and rate limiting. The payment service orchestrates the flow. The ledger is append-only. Choose a strongly consistent database like PostgreSQL. This orchestrator implements a saga pattern. It authorizes, records a ledger debit, then captures. If any step fails, it compensates by voiding the authorization. The idempotency key ties everything together. Testing a payment system requires more than happy path unit tests. You need integration tests against a sandbox, contract tests to catch API changes, and chaos experiments that simulate timeouts and duplicates. This consumer-driven contract test verifies that the payment service and gateway agree on the API. If the gateway changes a field name, this test breaks before production. It's your early warning system. The canonical payment flow. Persist the event first for durability, split into orders, charge the PSB, credit wallets only after success, then append to the ledger. Never update the wallet optimistically. This code shows the flow. Persist the event, split orders, charge the PSB, then credit wallet and append ledger only on success. If the PSB fails, you don't credit, avoiding ghost money. Every night, the bank sends a settlement file. Your job is to match each row against your ledger. Automate this matching and flag any mismatch. Never autocorrect. Human approval is cheaper than explaining a loss to the CFO. This reconciler reads the settlement CSV, joins on transaction ID, and alerts on any unmatched or amount mismatched rows. Missing settlement file triggers a critical alert. It's that important. This is the same issue we highlighted at the start. Here's exactly why that happened. The client software development kit generated idempotency keys using timestamps. Under Black Friday load, 2 requests got the same key. The capture endpoint lacked idempotency, so the gateway processed both, resulting in double charges. The fix: attach an idempotency key to every capture call, derived from the authorization ID plus a unique request ID. The gateway's idempotency store deduplicates retries. also replaced timestamp keys with cryptographically random server-side UUIDs. This is the exact line that caused the incident. Timestamp-based keys collide under high concurrency. Always generate idempotency keys server-side using a cryptographically random UUID. If two requests arrive in the same millisecond, they get the same key. The second request is silently ignored, but if the first fails, the second never retries. Always use a cryptographically random UUID. If you store balance as a mutable column, a database failover can apply the update twice, doubling the deduction. Always derive balance from an immutable ledger. Without a retry limit, a prolonged gateway outage causes millions of queued retries. When the gateway recovers, the flood takes it down again. Always cap retries and use exponential backoff. A team used DynamoDB with eventual consistency for their ledger. During a region failover, they lost committed payments because the last write wasn't replicated. For financial data, choose strong consistency. The article mentions Webhook Idempotency in passing, but doesn't detail implementation. Webhook endpoints must store the webhook event ID with a unique constraint to prevent duplicate processing. This is critical because payment gateways often deliver the same event multiple times, and double processing can cause duplicate refunds or ledger entries. Implement Webhook Idempotency by storing the event ID in a table with a unique constraint. If the event ID already exists, skip processing. This ensures exactly once handling of webhook events. The article recommends a 7-day TTL for idempotency keys. However, for subscription payments or delayed settlements, a longer TTL, e.g., 30 days, may be necessary to cover the full life cycle. Balance storage costs against the risk of double charges from late retries. Use a background job to archive expired keys to cold storage for audit purposes. Here are commands to diagnose payment issues. Check the idempotency store for key reuse, run reconciliation queries, and inspect logs for timeouts. Always correlate using the idempotency key. Let's run through some common interview questions. How to guarantee exactly once processing? Use idempotency key with unique constraint on every request. Difference between idempotency and unique constraint. Idempotency returns cached result. Unique constraint prevents duplicate inserts. How to handle authorized but failed capture? Retry with same idempotency key. If still fails, void authorization and dead letter. And a few frequently asked questions. What TTL for idempotency keys? Cover settlement lifecycle, typically 7 days for cards. Can I use retries for idempotency? Yes, with persistence and strong consistency, but prefer transactional DB for critical payments. How often to run reconciliation? At least daily, for high volume, hourly, or near real-time via webhooks. To recap, idempotency keys are your most important safety net. Use append-only ledgers. Pair retries with exponential backoff. Automate reconciliation from day one, and always choose strong consistency for financial data. Ready to go deeper? Up next, design a live video streaming system, then design an e-commerce platform, then design a content moderation system. Find them all at TheCodeForge.io. Thanks for watching. The full article and code examples are covered in detail at TheCodeForge.io.